From the IFIMAC Institute at Universidad Autónoma de Madrid, we would like to congratulate Anne Lullier, Ferenc, Krausz and Pierre Agostini for the Nobel Prize in Physics this year. As stated by the Royal Swedish Academy of Science, the award is given for the experimental methods that generate attosecond pulses of light for the study of electron dynamics in matter. An attosecond is a billionth of a second, so 10 to minus 18 seconds. So let's say 0, 17 zeros and a 1. And this is the order of the duration of the light pulses that were generated through the so-called high-order harmonic generation techniques that was developed over the years, and with the principal actors, these three great scientists. In order to understand it, since the construction of the first lasers in the late 50s, there was a race in order to get higher and higher intensities in the light pulses and shorter pulse durations. Already in the 80s and 90s, the availability of femtosecond light pulses, so 10 to minus 15, so 1,000 times longer than the attosecond pulse, already these time scales were enough to access, for instance, the nuclear rearrangements within the molecules. So it was possible already to have the so-called molecular movie. With the attosecond pulses, we can go further, and now we can even follow the electronic motion within the atoms and the molecules. So the techniques that allow this require a bit more of developing from the, let's say, the traditional developers of laser technology. And the main technique is called the high-order harmonic generation technique, that in a nutshell, what happens is after many works in strong field physics by the Pierre Agostini and Anne Lullier and collaborators, they discovered when rare gases were irradiated with an infrared light pulse, a coherent emission of light in the extreme ultraviolet regime was produced. Indeed, what they observed is that this emission was happening at the hot harmonics of frequencies, multiples of the frequency of the driving infrared field. And since these observations in the late 80s, there was a lot of experimental and theoretical work on trying to understand what is the mechanism that is behind. And after several tries, it was proposed a simplified model called the three-step model, which in a nutshell, when the infrared field starts to hit the atoms and we have, let's say, the amplitude starts to increase, what happens in the atom is that the molecular potential starts to bend, then the electron sees a barrier from which it can escape. So the electron is free in the continuum, and while the infrared field is still present, we can see that this barrier still is there. The electron still gets accelerated against energy. When the infrared field changes sign, what happens is that the molecular potential bends back, the electron is scattered back to the atom, and when we reach the zero of the field, the electron recollides with the atom and then emits a photon in the extreme ultraviolet, so really multiples of the infrared field that we have. And of course, along the infrared field, this process repeats every half a cycle. So what one observes is that every half a cycle, we have an emission of an attosecond pulse in this region. And this was the generation of the first attosecond train pulses. In order to characterize this light, there was also way more advances, and Pierre Agostini proposed the so-called rabbit technique, reconstruction of attosecond beating by interference of two photon transitions. And in 2001, they generated the first and characterized the first attosecond pulse train. In the same year, Ferenc Krausz was producing the first isolated attosecond pulse. And since then, of course, there has been a lot of work in order to see applications and discover new ways to access matter with these short pulse durations. This is where my research area belongs to, trying to answer these questions. What are the applications? I started my PhD in 2001 when the first attosecond pulses were generated in different labs in Europe, in France, or in Vienna and Austria. And we focus on applications where we can access the electron dynamics in gas phase atoms and molecules. Say we are working on the part 2 of this topic, while the Nobel Prize was given to part one, to how to generate these pulses. Of course, in these 2 decades, there has been quite a lot of proposals for new strategies to alter matter by exploiting these sources. One of the main examples is that, for instance, it has been experimentally demonstrated that it is possible to measure the time delay in the emission of electrons from matter from different cells. Let's say, if we think in the photoelectric effect, at the beginning it was thought that it was an instantaneous emission of the electron. This emission is not instantaneous. There's a delay that depends on the orientation of the molecule, or the energy of the electron when it goes into the continuum, or even the different cells from which the electron can escape. So you can imagine we are really accessing a very fundamental knowledge of matter. What is next, this is precisely the challenge. I mean, now we have revitalized motivation in order to keep exploring these new strategies to learn more about matter with an unprecedented spatial and temporal resolution.